Hey everyone, today we're diving into something that's right at the heart of software security and trust. We're talking about the quest for reproducible builds.
So let me start with a question for you. It sounds super simple, but trust me, the answer is, well, it's pretty wild. If you take the exact same source code and compile it twice, using the exact same tools, you should get the exact same program, right? Byte for byte, totally identical? Logically, you'd nod and say, yeah, of course. But what if I told you that's almost never what actually happens?
The reality is, more often than not, you end up with two completely different binaries. We'll call them X and Y, even though you started from the exact same place. Now, this isn't a mistake or a bug. It's a really fundamental challenge in software engineering, and it's the puzzle we're going to solve together in this explainer.
So how on earth is that even possible? This brings us to our first section, the build puzzle. We're about to unpack this whole situation that seems like a total paradox and find out what's really going on under the hood. The fancy technical term for this whole thing is a non-deterministic build. And as you can see, it just means that the output, the final program or binary, isn't guaranteed to be the same every single time. It's not a bug in the way we usually think of them, but more of a side effect, a result of all this hidden information that sneaks into the build process.
So, what is this hidden info? What are these little gremlins messing with our builds? Well, that's what our next section is all about. Let's look at the sources of digital chaos. These are the hidden variables that are secretly changing your final program.
What's so interesting when you look at this list is just how normal all this stuff is. The Linux kernel's own documentation points to things like timestamps. The build process often just stamps the binary with the current date and time. Then you've got the username and hostname of the computer doing the build. Yeah, that gets baked right into the version info. Even things like the file paths used for debugging or some randomly generated security keys can change the final binary. Every single one of these is a tiny, seemingly harmless detail that ends up making the output unique every single time. Okay, so at this point you might be thinking, all right, cool technical puzzle, but so what? Why does this really matter? And that brings us to the most critical part of this whole discussion, the high cost of mistrust. Because this isn't just some weird quirk, it's a massive security risk.
And this quote from the kernel documentation just nails it. It gets right to the point. If you can't reproduce a build, you can't verify it, period. You can't be 100% sure that the program you're about to run hasn't been tampered with, maybe by a compromised build server or some bad actor.
So here's the crucial takeaway. Without a reproducible build, a huge gap of trust just opens right up. You might trust the source code, you can read it, you can audit it, but you have no way to prove that the binary you downloaded is actually a faithful copy of that code. Malicious code could have been slipped in during the build, and you'd literally have no way of knowing.
Okay, so that's a pretty serious problem. But the good news is, the developers of the Linux kernel have come up with a really sophisticated response. Let's jump to our next section to see how they tackle this thing head-on with the kernel's toolkit.
What's so clever here is just how systematic their approach is. For every single source of chaos we saw earlier, the kernel build system gives developers a specific control. For timestamps, they can just set a fixed value using a variable, usually tying it to the source code's commit date. Same thing for user and host names. They even use special compiler flags to make all the file paths look the same, and they pre-generate randomization seeds so they're consistent every time. It's like a methodical campaign to just stamp out non-determinism.
And all this amazing work happening inside the kernel, it isn't happening in some bubble. It's actually part of a much bigger movement, one that's totally essential for our digital lives. This is all about building a more trustworthy future. See, the Linux kernel is a huge player in a global effort called the Reproducible Builds project. This is this massive collaboration between hundreds of open source projects. We're talking everything from operating systems to simple apps, all working toward the exact same goal, making it possible for literally anyone to independently verify that the software they're running actually matches the source code it claims to come from. So what's the bottom line here? It's that this work is foundational. Reproducible builds are an absolute cornerstone of a software supply chain that we can actually verify and, more importantly, trust. In an age where, let's be honest, our entire world runs on software, being able to trust it, that's not just a technical feature, it's an absolute necessity. So I'll just leave you with this final thought. The next time you download a software update, doesn't matter if it's for your phone, your computer, maybe even your car, just stop and ask yourself, how can I actually prove this is the real program? And the answer, as we've just seen, lies in this incredibly important quest for reproducible builds.